I will show you several homework problems. First problem is number 16. The blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency about 7.5 times 10 to the 14th power hertz. As you calculate wavelength in nanometer. Tell us frequency nu 7.5 times 10 to the 14th power hertz. As you calculate wavelength. So we learned at the beginning of this chapter, frequency times wavelength equals to light speed, where light speed, the number is 3 times 10 to the 8th power meter per second. So here tell us frequency, so we can calculate the wavelength lambda equal to C divided by frequency. So C is 3 times 10 to the 8th power meter per second. Frequency 7.5 times 10 to the 14th power hertz. Okay. So use the calculator, find out the value 3 divided by 7.5. Okay. So this will be 0.4. Exponent, division, subtract the exponent. 8 minus 14. Unit, hertz, actual meaning is per second. So cancel this per second. Left over meter. But here requires you in nanometer. So we have to convert this meter into nanometer. 1 nanometer equals to 10 to the negative 9th power meter. So not meter cancelled, left over nanometer. Right. So now divided by 10 to the negative 9. So exponent becomes minus negative 9, which is plus 9. Okay. Plus 9 added to here, total will be 10 to the 3rd power. 10 to the 3rd power, you can move this 3 places, becomes 400 nanometer. Okay, this is A. B. Also, you calculate the energy in joules of a single photon associated with this frequency. So we know energy for one photon equal to h times nu. H is a Planck constant. So during the quiz or test, I will provide you this value. Planck constant is 6.63 times 10 to the negative 34th power joule second. And nu is a frequency. Here tell us is 7.5 times 10 to the 14th power hertz. Hertz, the actual meaning is per second. So per second, cancel this second. Left over joule. So use calculator, find out 6.63 times 7.5, which is 49 0.725. Exponent, negative 34. 14. So multiplication is at. So negative 34 plus 14 is negative 20. Negative 20, but here 49 is greater than 10, right? Scientific notation, the regular number is less than 10, so we can move one decimal place, become 4.9725. Then add 1 to here, becomes negative 19. Well, since this is 2 significant, this is 3, so your answer can only keep 2 significant figure. Where this one is 7, greater than 6, so we round up 1, then becomes 5.0 times 10 to the negative 19th power joule. Okay. And this one is pretty straightforward. During the quiz or test, I will provide you for light speed and Planck constant. Don't worry, you are not required to memorize these constants. Let's say next one is number 29. Number 29, consider the following energy level of a hypothetical atom. E4 is negative 1 times 10 to the negative 19th power joule. E3 is negative 5 times 10 to the negative 19th power joule. E2 negative 10 times 10 to the negative 19th power joule. And the E1 level is negative 15 times 10 to the negative 19th power joule. A, ask you what is the wavelength of a photon needed to excite an electron from E1 to E4. Electron initially in E1 energy level. You want to promote this electron to E4. And this energy comes from a light. Ask you, what is the energy of the photon? Photon is a particle, consists light. The particle consists of light, we call photon. So ask you, what is the energy a photon must have? This means the energy of one photon. So energy of one photon, we just showed in number 16, is E equal to h nu. So this energy needed is the energy difference between these two energy levels for E1 to E4. So energy level, the energy needed is energy difference between these two. So E4 minus E1. And this E comes from light, from one photon. So E equal to h nu. E4, E1, both non-value. H is a Planck constant, so we can calculate the frequency needed. And here, let's take a look. Ask your wavelengths, right? So whenever we calculated this frequency, we can calculate the wavelengths. Or we can combine in one step. So wavelengths times frequency equals to C. So nu equals to C divided by lambda, right? So now E4 minus E1 equal to H times C divided by lambda. Then lambda equal to H times C divided by E4 minus E1. H as a Planck constant, the value is 6.63 times 10 to the negative 34th power, joule second. C is light speed, 3 times 10 to the 8th power, meter per second. E4, negative 1 times 10 to the negative 19. E1, negative 15 times 10 to the negative 19. This is joule. So joule cancel this joule. Second cancel this per second. Your unit will be meter. So again, this combined together, negative 1 minus negative 15 is 14, right? 14 times 10 to the negative 19th power. Then use your calculator. 6.63 times 3 divided by 14. 6.63 times 3 divided by 14. This will be 1.42. Exponent negative 34 plus 8 minus negative 19, which is plus 19. So plus 19 is together with 8 is 27. Then negative 34 will be negative 7. Unit is meter. And here ask you what is the wavelength, but then specify must be in meter or nanometer, so we can keep in meter. Or if you want, you can convert to nanometer. Convert nanometer times 10 to the 9, then will be 142 nanometer. So this here not required. Then take a look at B. Ask you, what is the energy in joules a photon must have in order to excite an electron from E2 to E3? So this time, electron initially on E2 energy level. And you want to excite this electron to E3. So to E3 is here. So clearly the energy needed is the energy difference between these two energy levels. So energy needed is the energy difference between these two levels. Right. Then E3 is negative 5 times 10 to the negative 19. E2 is negative 10 times 10 to the negative 19. So clearly, this will be 5 times 10 to the negative 19th power joule. This is the energy needed to excite the electron from E2 to E3. Then C, when an electron drops from E3 level to E1 level, this is from higher energy level to lower energy level, it will release energy. We call this atom under emission. Calculate the wavelength of the photon emitted in this process. So C is from E3 to E1. E3 electron initially on E3 energy level, now drop to E1, drop to lower energy level. During this process, will release energy, and this energy released is the energy difference between this and this. Since it's dropped from E3 to E1, so E1 is the final, E3 is the initial. So E1 is negative 15 times 10 to the negative 19. E1, E3 is -5 times 10 to the -19th hour. So their difference is -10 times 10 to the -19th hour joule. This is the energy will be released from E3 drop to E1. But here ask you calculate the wavelength of the photon emitted. So when when electron drop from higher energy level to lower energy level, emit a photon. And this photon's energy come from one photon energy is h nu, right? But here also is a wavelength. We need to convert the frequency into wavelength. So frequency times wavelength equals to c. So nu equal to c divided by lambda. Then lambda equal to h times c divided by e. Okay. H is Planck constant. 6.63 times 10 to the 34th power joule second. C is light speed, 3 times 10 to the 8th power meter per second. E, be careful, E we calculate is -10 times 10 to the -19th power. But the negative sign just tell us this is release energy. When we calculate the wavelength, don't put this negative sign there. Wavelength, no negative number, just put the absolute value. 10 times 10 to the -19 joule. So joule, cancel this in joule. Second, cancel per second, left over meter. It's the wavelength of the photon. So use calculator 6.63 times 3. This will be 19.89. Exponent -34 plus 8 minus -19, which is plus 19. 19.827. Then -34 will be -7 units meter. Okay. We can convert this into nanometer, but here didn't require, so you can keep here. If you want, you can convert to nanometer by times 10 to the 9. 10 to the 9 minus 7 is 10 to the 2. Then move 2 decimal place. Oh, actually, this will be -8. This is negative, yeah, 27, -7. But here, 6.63 times 3 times divided by 10 is 1.989. For the divided by 10. Then times 10 to the 9th power. Minus 7 is 2. 2 move to 2 decimal place is 198.9 nanometer. Again, here not required, so you can keep in meter. Let's take a look problem number 80. The ground state electron configuration listed here are incorrect. Explain what mistake have been made in each and write the correct electron configuration. Okay, here has a concept called the ground state. Ground state means naturally lowest possible state. So anyway, for you guys, always ground state of electron configuration. Okay. So first one is aluminum. Number 88. Aluminum. Electron configuration right here is 1s2, 2s2, 2p4, 3s2, 3p2. What's wrong here? Okay, so clearly this is wrong because 2p maximum can put 6 electrons there. Why not put 6? Since you still have electron left here, right? So you must put 6. Only out 2p6, then you can go to the next 3s2, right? So this is wrong. So this should be 1s2, 2s2 are correct. Then 2p6 and 3s2 also correct. 3p, nothing left. So this example tells us we must put enough electron on the subshell before you go to next octal. 3s. The aluminum total is let's see aluminum how many electrons. Sorry, aluminum actually is 13 electrons. 13 electrons, then 3p1. We should still have 1. Okay, take a look at the periodic table. Aluminum 13 electron, so we need this 10. We left over 1 electron in 3p subshell. Next one is boron. One s2, 2s2, 2p5. What's wrong? Boron, periodic table tells us boron only 5 electrons. And here, 9 electrons. And too much. So 5 electrons should be 1s2, 2s2, 2p, only 1. Only 1 electron left. Next one is fluorine. 1s2, 2s2, 2p6. Boron, too much. Too many electrons in 2p. Okay, so only 1 left in 2p. Fluorine, take a look at periodic table. How many electrons? Total 9. And here is 10. Also too many electrons, but in 2p subshell. So fluorine, 9 electrons should be 1s2, 2s2, 2p, or 5. Okay. Let me show you a couple more electron configuration and orbital diagram, even though these are not the assigned homework problem. First is R. We need to use a periodic table. Okay. Periodic table tells us there are 26 electrons. For R. So we need this chart, right? To write the electron configuration. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. 1s always first, then 2s, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s. Right, so according to this chart, we can write the electron configuration for R. So 1s2, 2s2, then 2p6. After 2p is 3s, 3s2, 3p6, then 4s2. So up to here is 20. Now 6 left. So after 4s will be 3d. So 3d maximum can place 10, but only 6 left. Then 3d6. Okay, so this is the electron configuration. Then orbital diagram, right underneath the electron configuration. So 1s only 1 orbital, 2 electron. In opposite spin direction, 2s also 1 orbital, 2 electron in opposite spin direction. 2p, 3 orbitals, 6 electron. So each orbital hold 2 electron in opposite spin direction. 3s, 1 orbital, 2 electron in opposite spin direction. 3p, 3 orbitals, each orbital holds 2 electron in opposite spin direction. 4s only 1 orbital holds 2 electron in opposite spin direction. The 3d, 5 orbitals. Five orbitals, each orbital hold 1 first. Each orbital places 1 electron first. Then the last one, 3d6, right? We have another one. Another one you can place into any one of these 5 orbitals. Any one of these 5 orbitals. But must be in opposite spin direction with the first one. Okay. This is R electron configuration orbital diagram. You must write orbital diagram right underneath each subshell. Without this electron configuration, if you only draw this orbital diagram, nobody can understand what this means, which subshell it is, which orbital this represents. Okay, so you must align electron configuration with the orbital diagram. Next one, copper. Here the table tells us copper has 29 electrons. Then again, use this chart. We can write electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 10, 29. Right? We expect 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 because only 9 left. But whenever you see 3d9, you need to be careful. This 9 becomes 10. So 9 becomes 10, and this one more electron comes from its neighbor 4s. This 2. becomes 1. This we learned in chapter 7, we call full field or completed field is more stable. We have this example, the PowerPoint slide, the last slide, right? So this completed field more stable, not expected 3D9, 4s2 3D9, but 4s1 3D10. Okay. Now we can easily write the orbital diagram. 1s is a 1 orbital, 2 electrons in opposite spin direction. 2p6, 3 orbital. Each orbital holds 2 electrons in opposite spin direction. 3s is only 1 orbital in opposite spin direction. 3p again 3 orbitals in opposite spin direction. Four S1 and 3D becomes 10, 5 orbitals. Each orbital holds 2 electrons in opposite spin direction. Okay, that's it for this homework. I wish everybody practice the rest of the assigned homework. And next Monday we will have quiz 7.